Hello physics students. In this video, you're going to learn how to analyze a couple scenarios where a moving charged particle experiences both the electric force and the magnetic force at the same time. And it turns out that the analysis that we've been doing for a couple years now on how to analyze situations with multiple forces, finding net force, that same analysis is going to serve us here. In other words, the magnetic force just behaves like any other force when you're analyzing the motion of something. And so let's begin with the topic where we have crossed magnetic and electric fields. Crossed meaning they're not lined up, they're at an angle to each other. So what I have here is a device that is basically a parallel plate capacitor. This is the positive plate, as we can see from the polarity of the battery, and this is the negative plate. And that creates an electric field from the positive plate to the negative plate, as you can see indicated by that arrow in the downward direction. I also have a magnetic field. Maybe it's caused by some current wires or maybe a permanent magnet, but it's making a magnetic field going into the board here. And in this case, what I've done is I've thrown an electron through this arrangement in this direction with a velocity like that. What I'm going to do is create a pause, and I want you to figure out the direction of the electric force, not the magnetic, in the pause. So go ahead and do that now. Okay, so hopefully you said towards the top of the screen, and the reason why is because electrons, negatives, feel a force in the opposite direction electric field. If this were a proton, it'd feel a force down. But it's not, it's an electron, so we can say F subscript E, okay? Now, I'm going to create a pause, and in that pause, I want you to figure out the direction of the magnetic force on that electron projected this way. Remember, it's one of the right-hand rules, so go ahead and figure out that force. Now, again, remember, don't just watch and wait, practice. So go ahead and do that now. All right, so that's this right-hand rule, not this one. This is for current and magnetic field. This is for finding force, okay? So I put my index finger in the direction of the electron's velocity, and then I have to have my three fingers pointed in the direction of the magnetic field, in other words, into the board like this, and you see my thumb points in the upward direction. That would be the force if this were a proton. But since it's a negative charge, it feels a force in the opposite direction of this, so I will add my arrow like that, F subscript B, okay? Now, the electric force is a constant, and it does not change with the velocity. All it is Q times E, charge times electric field. But the magnetic force depends on the velocity. The faster I go, the more the magnetic force is. The slower I go, the less from QVB sine theta. So if something is going relatively slow compared to some, well, I'll talk about it later. If it's going too slow, what will happen is this arrow will be smaller than this constant arrow here because the velocity is smaller. So the electrical force will dominate and tend to curve this up. There'll be an acceleration upward. If the velocity is too large, then this arrow will become longer than FE, so there'll be a net force in the downward direction causing a deflection like this, almost like a projectile thrown sideways. So magnetic force bigger. If the velocity is just right, it will be large enough, just large enough to match, the magnetic force will match the electric force, they'll be equal, and so the net force will be zero. It'll travel, this electron, constant velocity, straight line path. So we want to now analyze that undeflected path. So for this path, the net force is zero. That means the force have to balance, the magnetic and electric force have to be equal. Filling in the pieces, the magnetic force is QVB sine theta, as we learned in an earlier video on this topic. And in the previous topics, we learned the electric force is QE. What we're going to do is solve for the velocity, or the speed, I should say. The charge drops out. Sine theta, why was it 90 degrees? Because if you look at the velocity in the magnetic field here, they are 90 degrees to each other, so that goes away. And solving for V, the electric field over the magnetic field, that's the exact velocity, or I should say speed, I need to shoot this so it passes through undeflected. Slower than that, faster than that, exactly that. So I'll create a pause to allow you to copy this down. All right, let's move on. We can basically eliminate the electric field out of this formula because we know from this expression that the electric field is determined by the voltage that I put on this capacitor. And from this expression, I could use this. I don't have to integrate electric field because the electric field is constant over this path, so I could just say voltage of the electric field times distance. Solving for electric field, I get voltage over distance, and then I can now substitute that in here, right there for electric field, and there's an expression for the speed I need to pass through undeflected based on the voltage, the magnetic field, and the separation between these plates. So I'll create a pause to allow you to copy this down. All right, what we're going to do now is move on to an application of this. One of the ways that you can measure magnetic field is with what's called a Hall probe. And so the Hall probe does a couple things. It measures magnetic field, and it also confirms that it's really electrons that flow in an electric circuit, not protons. Remember, most of the time we pretend protons are flowing, and then later we say, okay, no, the electrons are going the opposite way, and most of the time it causes no problems in our analysis. This is the one time in the course where you must analyze the phenomenon knowing that electrons are moving, not protons. If you analyze the phenomenon with protons, you'll get the wrong answer this time. So here it is, the Hall effect. What I do is I have a voltage source over here. It's going to pass a current through this bar of metal. It could be copper, whatever. And so you see the wire, one wire connected to the top of the bar, one wire connected to the bottom, and I have an ammeter here to verify which way the current's going. The bar has a certain cross-sectional area and a certain width to it. And in that bar, there's a magnetic field. I picked it to go into the board. I could have it coming out of the board, doesn't matter. So here's what happens. Because there are electrons, and for now we're going to definitely say they're electrons, flowing upward like this in the presence of a magnetic field, there is a force that acts, a magnetic force. So once again, I'm going to create a pause to allow you to practice the right-hand rule to figure out the force on this electron here. So go ahead and do that now. All right, so you put your index finger in the direction of velocity like this, and then I have to turn my fingers here so that they align with the magnetic field. So I'll swivel my wrists like this. My thumb points to the left, but it's an electron, so it feels the force the opposite way. So this is the magnetic force to the right. And you could have figured that out, that it deflects from the right from the minuses I put over here, right? So, but that's how you do it with the right-hand rule. And then what happens, because a bunch of minuses, electrons, they get shifted here, it's going to leave this side of the bar positive. And that, therefore, creates an electric field that points from plus to minus. And since the electric field points to the right, that creates an electric force in the opposite direction because we're dealing with a negative charge. And once again, we have these two forces that balance in this bar, and the electron flows straight up undeflected because of the deflection early when I turned on the circuit. Now, as I said, this proves that electrons must be flowing in a circuit. That's one of the things of the Hall effect. So we can't see this, right? We don't know what's happening, but we can verify in this experiment how. Let's suppose we said, oh no, protons are coming out of this end of the battery, not electrons. So current is really protons going like this. So that's what I have diagrammed here. Now, the protons are going down, hypothetically. Let's use the right-hand rule to figure out the force on, the magnetic force on those protons moving down. So I'll create a pause, allow you to do that. So here we go. I put my index finger in the direction of the velocity, right? So there it is. Now these three fingers have to align up with the magnetic field, so I got to turn my wrist like this, and you see my thumb points to the left. And so that is the force on a positive, which this is. So that would indicate if there were protons flowing, the charged particles should be deflected to the left, to the right. And that means that this end will be positive and this will be negative, opposite over here. Which is it? All I need is a voltmeter. So I got a couple voltmeter probe wires. Imagine this is connected to a voltmeter. And I go like this and I say, oh, I believe that it's really protons flowing. Let me measure the positive over here, volts. And let me measure the negative on this side. And I touch and my voltmeter reads negative. It says you have it backwards. It would read positive if it were protons, but it's electrons, so it reads negative. So then I switch my wires and I go like this, and it reads positive voltage on the left side. And so I know it must be electrons, not protons, in an electric current. Okay, so verification that it's electrons flowing in a circuit. That's one application of the Hall effect. So let me give you a moment to copy these notes down to the best of your ability. Notice I like to do this, projecting the word area onto that surface. Fun for me, but you don't have to do that. So just copy this down in this pause. All right, there are more applications of the Hall probe and the Hall effect. So let's take a look at those now. What else can the Hall effect tell us about circuits and magnetism and whatnot? So all right, maybe I'll try and stick like this. So the first thing, when this equilibrium is established, once again, as you can see, these electrons deflect until the next set come and the forces balance again. So I could say the magnetic force, again, is balanced by the electric force, as we see in the diagram, undeflected path. Again, QVB sine 90 degrees. Why 90 degrees? Velocity is going like this, and magnetic field's going in. Velocity, magnetic field, 90 degrees to each other. That's where that comes from. And the electric force is Q times that electric field that eventually forms because of deflection electrons. Again, the charge goes away. And what I can do is I can solve for, but note that the voltage, the electric field creates a voltage. Okay. What voltage? Well, as you saw, I have these voltmeter probe wires. So the voltage is going, not this voltage that creates the current, but the voltage I'm measuring from one side of this bar to the other. And so that is electric field times the distance, which is the width of the bar. I'll just drop these right here. So I could say delta V equals E times W. In other words, take this E and plug it into here, and I get VB equals electric field delta V over W. So couple variables here. These I can measure pretty easily. But what about the speed of these charged particles or the magnetic field? Well, one of the things I could do, what is the speed of an electron? I mean, we can't see these things. They're submicroscopic, even smaller than microscopic. So how can we figure out what the speed of an electron is in a circuit? Well, remember in circuits topic 1, we defined the current density as the current over the area. I could write A, but I'll write area once so that you don't confuse it with like amps. So it's the current over the area, but it's also N, NeV. What are these terms? This is the charge concentration of, or I should say the number of current carrying particles in every cubic meter of the metal. So this is the amount of electrons per meter cubed. This is, of course, the charge 1.6 times 10 to the minus 19th. And what I'm going to do is solve for V and get rid of that out of that equation. In other words, V, the speed of these particles, if I know the current, it'll be the current divided by the number of electrons per cubic meter, the charge of each electron, times the area of this bar of metal. And I'm going to plug that in now to this formula right here. So in other words, I, over NEA times B equals delta V over W. Okay, so here is as far as I'm going to go. So first, let me create a pause to allow you to copy these notes down. All right, so why is this important? Well, one, it might be important for you in May on the AP. You might have to do this as part of the curriculum. But in terms of humanity, what did it allow humanity to figure out? Well, in addition to the electrons being the things that carry charge, if you solve this equation for B, what you have is what's called a Hall probe. So if we were in class, I would hold up a sensor that we can hook up to the Lab Pro that can measure magnetic field. What that sensor does is it has something like this in here. And then the Lab Pro, the electronic device, would measure the voltage from here to here, because that's easy. We have voltmeters to do that. It would know the width of the conductor in the Hall probe because that's what you manufacture. You try and manufacture it to a certain width and a certain area. So know the width, the area. This would be known. You could look this up on the internet or in tables. We know the charge on an electron. And it would measure the current. So it would measure the current and the voltage. And through software, it would calculate and give you the magnetic field. So the Hall effect is one way you can make a Hall probe to actually measure magnetic fields in a lab. Boom, boom, boom. You're walking around with this little sensor and you're measuring magnetic field. That's nice, okay? The other possibility is suppose you solve for N. Because you work in a lab and you're interested in knowing, so then what you know is the electron's density, the electron density in a cubic meter for a particular metal. So, again, how do we determine the electron density in metal? Start counting? You can't even see these things. You can't even touch them. So you do a Hall experiment, and this time you use a known magnetic field. You measure the voltage for given width and area of a conductor. You know the charge on an electron. You measure the current, and you solve for this, and boom, you know exactly from this experiment how many electrons are packed into a cubic meter of metal. So also very useful. So very useful thing, this Hall effect and a Hall probe. So let me create another pause to allow you to copy these last couple little bullets down. Okay, so that was analyzing charged particles moving through a magnetic field with both an electric and magnetic field. And so then there's an electric and magnetic force that balance, and then we can figure out the speed for an undeflected path, or we can figure out from the Hall effect the magnetic field or the charge density or the electron density in a metal. So I hope you enjoyed the video, and I'll see you in the next video.